Fine-grained sediments are sometimes called clays. But as we have discussed in other segments where we were talking about clay soil genesis, the word clay really means two different things. So the same word is used with two different semantics. One is to talk about size, and typically it varies with some organizations, but this is when the size is less than 2 micrometers. And the other one is to talk about minerals. And these are very unique minerals. They are also called phyllosilicates, and they tend to be layered. That is the meaning of phyllo, meaning pages, and silicates because one of the components is silica. This is where we're going to focus today. And we're going to advance in multiple scales. We're going to start at the atomistic scale to talk about the building blocks. We're going to put these building blocks to form these sheets. We are going to stack the sheets to form a sandwich, which are going to form the layers, and by now we are going to have already pretty much the final structure, except that how these layers are bonded together will determine the actual name of the clay mineral. But we are not ready yet. At some point, which we are not going to cover today, these multiple particles come together and they bond together into something that we're going to call tectoids, forming structures that look pretty much like that. And they move together as bunches, and sometimes they deform together as bunches. Those are tectoids. So to clarify, here we are pretty much at the angstrom scale, nanometer scale. From the angstrom scale, we're going to build height to form the sheets, but when we put them together, now we are at the nanometer scale. And by the time we reach tectoids, we're going to be at the micrometer scale to form the soils. So when we talk about clay soils, we are really looking at this range, but what it is so important to recognize that the properties at the meter scale beneath our foundations reflect the interaction between tectoids, which, by the way, they carry the properties of the layers all the way down to the building blocks. Now, you may wonder what other components are here in the small size. Well, there are some crystals that have precipitated, and you are going to see, for example, lots of pyrite crystals and calcite crystals in the sediment, and diatoms are in this scale. And many of the fly ash components from thermogenesis are also found at that scale, and these are not clay minerals. They are clay-sized particles, which are of chemo-origin, bio-origin, biogenesis, or thermogenesis. But once again, these are not clay minerals. So let's come back to build clays from the bottom up. There are two building blocks, like the fundamental bricks of our system. One is a silica tetrahedron, and we make a triangle, and then we connect the vertices to the other vertex, where at the center we have a silicon with 4 positive charges. And on the corners we have oxygens. Because oxygens have valence 2, this system is clearly not electrically neutral. So we'll take care of that in a second. The other block is an octahedral structure. So we start from looking at the cross-section of the octahedral structure, and then we're going to put the corners at different elevations so we can visualize the structure. Now, in this octahedral structure, as you can see, it has 4 faces to the left and to the right. There will be hydroxyls on each corner. We have 6 hydroxyls, and at the center we have aluminum. Once again, it appears that the system is not electrically neutral. But now we're going to assemble sheets by putting these elements together. And so we take the silica tetrahedron, and looking at it from the top, it will form a hexagon where we have a silica tetrahedron and imagine that it's sticking up or down from each of these locations, and this keeps coordinating with the neighbors, and now the oxygens are shared, and because they are shared, I managed to neutralize the charge. In the case of the aluminum octahedron, it's more complex because they actually share an edge. So in the next presentation, I'm going to show you drawings that are already made coming from molecular structures, where you will be able to visualize this layer. But this layer is also going to form hexagons. And these hexagons can sit on top of these other hexagons to form the layers. So this is the silica layer, or the silica sheet, while this one is going to call the aluminum octahedral sheet, which, if it is aluminum at the center, is called gibbsite. To avoid carrying all these atoms along the structure, we're going to simplify, and we're going to say that this looks like that. And why? Because you can see there the tetrahedron, and this one, the gibbsite, we're going to represent it as a rectangle. And now we have the key layers that are going to form the sandwich of these phyllosilicates. So now we're going to stack them together to form layers, and the simplest one is 1 to 1. In other words, 1 gibbsite and 1 silica tetrahedron layer, and this is called kaolin, kaolinite. We extracted from mines, kaolin mines, meaning that most of it is kaolinite, but there may be other components. The other set of sandwiches are going to be 2 to 1 sandwich. And this 2 to 1 sandwich, the fundamental one is 1 silica tetrahedron, 1 gibbsite layer, and another silica tetrahedron. And this is montmorillonite. And sometimes we call them bentonites because we recover them from bentonite mines, where there will be not only montmorillonite, but there may be other components. Now, the story gets more interesting because now we can sandwich 2 montmorillonite layers, which are typically connected one to each other with sodium and calcium. Now we can connect them with potassium. So if we take a 2 to 1 layer and we connect them with potassium in between, potassium is a small and quite strong Coulombic bond with the surface. So if we put potassium here, these are potassium ions. Now it's also a 2 to 1 sandwich, but stack of these sandwiches, and this is called illite. Now, if instead of putting a 2-to-1 sandwich on top of another connected with potassium. I would do something similar, but in between I put also an octahedral sheet, but this octahedral sheet will be quite unique. Instead of having aluminum, it will have magnesium, which is positive 2. And this layer now is not called gibbsite, it's going to be called brucite. Then, when I make the layer complete, what I have is chloride. Now, for lack of space, I didn't complete this, but a kaolinite layer, which is probably around 7 angstroms, begin adding up the heights, and this is going to be about 7 angstroms. It's never like that. It's stuck on top of another kaolinite layer, and on top of another one. So they form booklets, and they come together like that, and probably with some hydrogen bond in between, bonded together. And in order to break those bonds, to separate them, you really have to beat the clays, and that's what the mining company does in order to increase the exposed surface area, for example, to make latex paint or to cover paper. In the case of montmorillonite, the next layer is going to be bonded with sodium and calcium, typically sodium or calcium, and that depends whether you have a sodium bentonite or a calcium bentonite. But water will get in and will hydrate that surface. Now, when we get to illite, this bond is quite strong, and water cannot go in and hydrate it, and so illite doesn't want to expand. So while montmorillonite is quite expansive because it's willing to hydrate, and it becomes a swelling clay, illite is much more stable. There is some swelling, but it doesn't really fall into what we would classically call swelling clay. These are the fundamental family names for clays, and within each of them, you are going to find many other characteristics, from the mica clays to the halloxites to vermiculites, etc. But these are the essential structure of clay minerals, which you start with building blocks, which are basically silica tetrahedrum and aluminum octahedra. You put them together forming sheets, and they come and they stack to each other, forming 1-to-1 sandwiches or 2-to-1 sandwiches. And depending on how these sandwiches come together, we have the different families of clays.